Hello, and welcome to my mini JavaScript project designed to demonstrate fuzzy logic. This week, I've decided to try something a little humorous, i.e. not meant to be taken seriously, and that's a dating website. Well, it's the bare bones of a dating website, as it only contains 14 people on its books, 7 men and 7 women, and matching only takes place on the basis of height, build, i.e. slim, medium or fat, and age. I should point out that I have absolutely no experience of dating on the internet or otherwise, so this is really just an excuse to demonstrate fuzzy logic more than anything else. Treat it as nothing more than a bit of fun. Here's the main screen that you see when you run the program. You are asked whether you're looking for a man or a woman, and you need to pick a particular height range, short, medium or tall, a build range, slim, medium or fat, and an age range, young, middle-aged or old. In each case, you can specify how important each choice is. For instance, you might want a slim partner, but aren't particularly fussy about it. In that case, you can set the importance of that row to somewhat important or unimportant. Once you've made your choices, you click on Find a Partner, and the program will score all the men or all the women against your criteria and list them on the screen, together with a matching score. The higher the score, the more the person matches what you specified. The screen itself is formed using a simple HTML table as shown. I've shown the row for choosing the height range of the person. Clicking on any of the radio buttons sets the variable height to 0 to select a short person, 1 for a medium person, and 2 for a tall person. The row to select a man or woman contains radio buttons to set the variable seeking to 0 if you're looking for a woman, or 1 if you're looking for a man. There are also a set of radio buttons to specify how important the height of your partner is. These set the variable height_i, I for importance, which is set to 0 for very important, 1 for important, 2 for somewhat important, and 3 for unimportant. For both these sets of radio buttons, default values are specified using the checked attribute, although this was just done for convenience, so that the program wouldn't have to check to make sure that the user had chosen an option in each case. Similar rows exist for build and age, except they set the variable build to 0, 1 or 2 to indicate slim, medium build or fat, and the variable age to 0, 1 or 2 to indicate young, middle-aged or old. Variables build_i and age_i are set in a similar manner to indicate how important these factors are. Although it doesn't appear on the screen, a division called results is set up beneath this table to hold the final list of names as presented to the user, together with the final score for that person. This is the function I use to fuzzify the height values of the people in the database. I have measured the heights in inches. Sorry if you prefer meters and centimeters, I'm a feet and inches guy. And, according to my simple metric, short people are less than 66 inches in height, tall people are more than 68 inches, and medium height people somewhere between 60 and 74 inches. This graph is encoded in 4 arrays. The array change_PTS give the height values at which some change happens, i.e. a person starts to be considered as tall or stops being considered as medium height or whatever. It has a dummy value at each end, 0 at the lower end and 100 at the upper end, just so that we can consider all the height ranges. Nobody could possibly be 0 inches tall or 100 inches tall, which is well over 8 feet. The array short vowels gives the degree of shortness of anyone with those particular heights. So a person of height 60 inches has a short vowel score of 1, but a person with height 66 inches has a short vowel score of 0. Arrays medium vowels and tall vowels enclose the particular transfer function that gives a medium height score and a tall score for that particular person. In this way, those 4 arrays encode the exact details of the graphs that you see above, and given the exact height of a person, they can translate it into a score for shortness, medium heightness, and tallness. Similar arrays exist for build and age. Build is specified as a waist measurement in inches, and given a particular waist measurement, a person can be given a score for slimness, medium buildness, and fatness. Age is simply measured in years, and another set of arrays will assign a score to a person for youth, middle age, or oldness. At the start of the JavaScript, the arrays are set up that encode the data for the 14 people in the database, with that number being stored in the variable numNames for convenience. You can see their names and genders, their heights, their waist measurements, and their ages stored in the appropriate arrays. However, those data values are only useful to convert into scores for the different attributes. The arrays short, medium height, and so on will contain scores for each quality, calculated according to the graphs that I showed you a while back. So while Fiona has a height of 68 inches, we are only interested in her score in arrays short, medium height, and tall. To what extent can she be described as short, of medium height, or tall? Once we have done that translation, her actual height becomes irrelevant. At this point, I also set up the default values in accord with the radio buttons initially checked in the HTML above. Indeed, directly after declaring the above arrays, we fill them by calling three functions: process heights, process builds, and process ages. I've shown process heights on the screen here. The other two work in a similar way. You will recognize the four arrays that define the transfer graph. A for loop with counting variable p per person goes through each person in turn, and within it, another for loop goes through each of the possible height subdivisions, from 0 to 60, from 60 to 66, from 66 to 68, and so on. If the height lies within that range, then it is turned into a shortness score, a medium heightness score, and a tallness score. The variable frac indicates how far through that subdivision of height range the exact height is. If a person had a height of 63 inches, for example, and the range being considered was 60 to 66, then that height will be exactly halfway through the range, and frac would come out as 0.5. Of course, this fraction might not be necessary at all. For instance, if the range considered was 74 to 100, then the exact heights of 75, 77, 79, or 89 for that matter, will produce identical scores for each of the three qualities. We've found the correct range for the person's particular height, so the shortness score is calculated by taking the shortness score of the bottom end of the range, 0 or 1, depending on what that range is, and adding on the appropriate fraction of the difference between the ends of the range. This fraction might be negative if the graph sloped down at that point. For example, if the exact height was 63, then the correct range would be 60 to 66. The shortness score for 60 is 1, meaning that such a person is definitely short, but this drops to 0 as that range approaches 66. The line of code that calculates the shortness score for 63 subtracts 0.5 from the initial 1 to give a final shortness score of 0.5. This all sounds a bit convoluted, but try a back-of-the-envelope calculation on various heights, calculating the final scores produced for short, medium height, and tall in each case. All those calculations are carried out before the user has clicked on Find Person, as they are independent of the user's choices. When the user clicks on Find Person, the individual scores must be combined along with their importances to give each person a final score. The variable s is set to be an empty string. This is where the final list of names and scores will be built up, ready to be copied into that division of results on the screen. A for loop goes through all the people in the database, only considering the ones of the gender that the user is seeking. For each of these people, the value of height is considered. This, you will recall, is the height range that the user chose, 0 for short, 1 for medium height, and 2 for tall. If the user picked short, then the shortness score is the one that is weighed up by the function score, and the other two are ignored. Similarly, if the user picked medium height, then the value for medium heightness is the one needed, and if the user picked tall, then the value for tallness is considered. Whichever value is needed, the final result, adjusted for importance, is stored in the variable height score. You can also see on the screen the switch statement that takes only one of the build ranges, whichever one the user chooses, weights it for importance, and stores it in build score. A similar switch statement, which I haven't bothered to put up, takes the three age range scores, throws all but one of them away, and waits the remaining one to give the variable age score. Oh, wait, there it is. As you can see, it has exactly the same structure as the previous two, but deals with ages rather than heights or builds. Having obtained these three adjusted scores, the final score for that person is found simply by adding them together. Then the name is added to the string together with the final score, and once every appropriately gendered person has been calculated, the list is displayed on the screen. Of course, the vital work is performed by the function score. This takes two parameters. Firstly, the quality range, short, medium height, tall, slim, medium build, fat, and so on, and the importance factor that goes with that quality. This was the variable with the I suffix to indicate that it represented importance. Looking at the switch statement for ages there, you can see that the three calls to the function score, the quality passed is different in each case, young, middle-aged, or tall. But the second parameter is the same in each case, age_I, meaning how important is the age range. In fact, the function score doesn't carry out any mathematics on that quality value at all. It uses it as another variable to be put through a transfer function to give an adjusted score. Look at the graph on the screen. The input quality, I've chosen the build here just to ring the changes, is compared to the 4 lines that you see on the graph. The horizontal line marked unimportant means that if the user has specified that build simply doesn't matter, then the adjusted score returned is the maximum of 1, regardless of the build. If build is somewhat important, then any build value less than 0.3 will give an adjusted score of 0, and any build value above 0.6 gives an adjusted score of 1, with intermediate scores lying between these extremes. For example, if the build value was 0.45, as shown, halfway between 0.3 and 0.6, then the adjusted score will be 0.5. Similarly, quality values have to be above 0.6 to match the level of important, even partially, and above 0.9 to match the level very important. A build value of 0.45 would give an adjusted score of 0 if the build was considered either important or very important. The shapes of the original transfer function have become totally irrelevant by this stage. While qualities such as short and slim peaked low down on their ranges and dropped off towards the higher end, and qualities such as medium height or medium build peaked in the middle, tailing off at both ends, by the time we reach this stage, all we are interested in is the strength of the basic scores, whether that's for slimness or youth, or shortness, or fatness, oldness, or tallness. That's why the non-horizontal lines on the graph you see only slope one way. And here's how the function score works. Again, it's just a switch statement, with the appropriate statements being called depending on which level of importance was chosen. Each clause of the switch statement corresponds to a coloured line on that graph you just saw. Okay, let's give the thing a trial run. I'm seeking a woman. Click. How tall? Well, I'm not particularly tall myself, and I wouldn't want her towering over me, so I'll say medium height. How fat? She wouldn't need to have the figure of a stick insect. I like my women to have a bit of meat on them, something I can really get hold of. But at the same time, I don't want a woman who's let herself go, so I'll say medium build. There you go. How old? Well, I like my women to be somewhat mature, something of a MILF, if you like. So let's say middle-aged. As for the importance levels, well, I'm not fooling anyone really, am I? As long as she's female and got a pulse, she'll do me. So I'll set the important levels for height and build at somewhat important, and rank the age as totally unimportant, just to ring the changes. Right, let's see who my dream woman is. Well, curiously, all the figures have turned out to be exact whole numbers. Normally you expect to see a few more decimal values in among that lot, as people are often located at the changeover points for the ranges. Indeed, two ladies, Sandra and Diana, have perfect scores of 3. It's just a shame that none of these people actually exist, and are all just random figures that I entered into the computer program. Still, it's nice to pretend for a while. And there you have it. I'm sure you can see several ways in which this mere skeleton of a program could be improved. For example, at the moment, you are limited to choosing only one range in each group of 3 presented. You could choose a slim partner, or a partner of medium build, or a fat one, but you can't specify more than one range, say either slim or medium build. It's an easy matter to replace the radio buttons with checkboxes, and the additional processing wouldn't be too arduous. You would need to combine scores using the formula for OR that we saw during the lecture. Try altering the figures provided for the people to see what difference that makes to the final scores. You should also change the changeover points for the different ranges to fit what you think better represents those ranges. Also, at the moment, the final results are just displayed in the order in which they're calculated. You might like to get the program to sort them so that the more promising candidates appear first in the list. Finally, the procedure for applying the importance has a sort of ad hoc quality about it. If someone specifies that a tall partner is required and that it is very important, then possible short partners can still score highly if they match the other qualities well. I'm sure a person who is adamant that he or she wants a tall partner would not take kindly to being paired with somebody less than 5 feet tall, even if that person matches all the other criteria well. I'm sure you can come up with a better method of applying importance. Since there is nothing standard about fuzzy logic, one solution is just as good as another, providing it does the job appropriately. And that's the end of the project. As usual, I've included a link to the lecture about fuzzy logic in the description below, as well as a link to the project on my own website, if you want to download it. Next week, I shall start the far more interesting topic of game playing. That's something to look forward to.